Welcome, Voyager. Before we begin our adventure, if this kind of journey speaks to you, if the quiet mysteries of science and the mind stir something deep within, a like, a comment, or a simple subscription makes a world of difference for a small channel like mine. It helps keep this space alive and brings this gentle curiosity to others who might be searching for it too. So relax, open your mind, and allow yourself to drift beyond what you've known as we contemplate tonight's cosmic mystery. There is a silence in the universe so deep, so absolute, that not even light can escape it. A place where time slows, where space folds like fabric under weight, and the very laws of physics begin to tremble. They are called black holes, but they are not holes. They're not empty. They're not dead. They are the collapsed hearts of ancient stars, wrapped in the deepest gravity the universe can create. They are wounds in space-time, and they whisper with the weight of everything that has ever fallen in. And tonight, you're going to fall. Not in fear, but in wonder. Not into darkness, but into mystery. So take a breath and let yourself go. Because at the edge of reality, there is no ground to catch you. Only the pull of a star's final breath. Only the slow unraveling of what you once thought was real. This is the story of what happens when you fall into a black hole. But it is also a story about space and time and the strange bending of truth that occurs when gravity takes the stage. You'll begin at the outermost edge where starlight still shines, and from there we drift, past the event horizon, into a realm where clocks break down, and even the idea of before and after becomes slippery. Somewhere beyond that silent veil lies the singularity, a place where everything collapses, or maybe everything begins again. So lie back, let the pull of wonder be the gentle current that guides you towards sleep. We are drifting now toward the most extreme frontier of science, a place where the map dissolves and all that remains is falling. At first it was light, not just any light, but the radiant blaze of fusion, a stellar furnace igniting in the dark, born from dust, pressure, and time. A star, one among billions, yet in its own sky, the centre of all things. It began as a cloud of gas adrift in the spiral arm of a galaxy, cool and slow and shapeless. But gravity is patient. Gravity pulls, and over millions of years, atoms of hydrogen drew together into a swelling mass. The pressure mounted, the centre grew hot, then hotter still, until the laws of physics had no choice but to relent. Fusion began. The star was born. From the outside, a star is serenity, a steady glow, a soft beacon of warmth. But beneath its luminous skin lies a war, a perfect, elegant standoff between two cosmic forces. On one side, gravity, relentless and hungry, always pulling inward. On the other, radiation pressure, born from fusion at the core, pushing outward with equal resolve. As long as these two forces remain in balance, the star lives. It shines, and for millions, sometimes billions of years, it holds that delicate equilibrium, pouring light into the void. But all fuel burns, and even a star, magnificent as it is, has limits. As it ages, it fuses hydrogen into helium, and then, if it's massive enough, it pushes onward, igniting heavier and heavier elements in its heart. Helium to carbon, carbon to oxygen, oxygen to neon, then silicon, and finally, iron. But there, the process halts. Iron is the dead end. Fusing iron consumes more energy than it releases. The furnace goes cold, and in that moment, barely a whisper in cosmic time, the balance shatters. The radiation falters, gravity wins. There is no warning, no flicker, no tremble across the sky. One moment, the star is a titan of radiance, burning with the brilliance of 1 billion nuclear bombs per second. The next, it is betrayed by its own chemistry. The iron building up in its core does not sustain the fire. It suffocates it. The fusion flame dims, and then, like a breath caught in the throat of the universe, it goes out. And with that, gravity begins to fall unchecked. The star's outer layers, vast oceans of gas hundreds of thousands of kilometers deep, suddenly lose their footing. They begin to plummet inward, rushing down with unimaginable violence, accelerating toward a core that is no longer resisting. And at the centre, something more terrifying begins to happen. The core itself, a ball of iron perhaps the size of Earth, begins to collapse. In less than a second it implodes. The atoms inside are crushed together under forces so intense that the very nature of matter begins to change. Electrons are forced into protons, creating neutrons. And in the process, the core transforms into something far denser than anything we can see or touch in everyday life. A neutron star is born, or in some cases, something even darker. But before we reach that threshold, before the star disappears entirely, there is a moment of apocalyptic release. The outer layers, now free-falling, strike the rebounding core like a hammer blow. The result is one of the most powerful events in the cosmos, a supernova. The star tears itself apart. For a brief time it outshines its entire galaxy. It blasts material across interstellar space, seeding the cosmos with the heavy elements it forged in death. Gold, uranium, the calcium in your bones, the iron in your blood. We are made from the remnants of these celestial suicides. Every atom heavier than hydrogen was born in a furnace like this and scattered by a final, fatal breath. But not all of the star escapes. Some of it continues to fall. Deeper and deeper, beyond the neutron star threshold, past even that extraordinary density. If the original star was massive enough, perhaps 20 or 30 times the mass of our Sun, then not even the degeneracy pressure of neutrons can stop the collapse. There is nothing left to resist. The infalling mass is doomed. And in that collapse, an event horizon forms, the point at which escape becomes impossible. A boundary not marked by light, but by fate. The black hole is born, no explosion, no flash, just the sudden silence of the cosmos. What does it mean to fall with no end? To collapse so completely that even space itself caves inward. This is not just the death of a star, it is the birth of a new kind of reality, a place where our rules no longer apply, a place shaped not by light, but by gravity at its most extreme. When a star crosses that threshold, when it folds in on itself so thoroughly that nothing, not even the light it once shed, can climb free, it becomes a black hole. But that phrase, simple and compact, does not capture what has truly been created. This is not a hole, it is not an object in the ordinary sense. It is a region, a domain carved into the fabric of space-time itself, a shadow with mass, a presence that cannot be touched, only orbited. From the outside, a black hole appears deceptively still. It is defined by its event horizon, a spherical boundary surrounding the collapsed core. This horizon is not made of anything material. It is not a wall. There is no surface. And yet it is a threshold that marks the limits of our universe's ability to send information back out. Once crossed, there is no return. Not for spacecraft, not for light, not even for time as we understand it. And this, perhaps, is the most disquieting truth. Black holes do not merely trap matter, they trap causality. The normal flow of cause and effect is twisted, contorted, and ultimately severed from the universe beyond the event horizon. From the outside, an object falling into a black hole appears to slow as it nears the horizon, its motion drawn out like taffy across time. It never quite vanishes. It simply redshifts, fading to black, asymptotically approaching the edge of nothing. But for the one falling in, the story is different. There is no pause, no hovering at the brink. You cross the event horizon in finite time. No flash, no sudden shift. The laws of physics at first feel eerily familiar, but the deeper you fall, the stranger they become. Space itself begins to curve in directions that no longer have meaning in human thought. Distances contract, time accelerates, directions lose their usual relationships. Inside the black hole, all paths, no matter which way you move, lead only one way, inward. Down, always down. Not into a pit, but into a singularity, a point of infinite density, where the curvature of space-time becomes so intense, so absolute, that all our equations collapse. Here, gravity is no longer a force, it is destiny. It is the shape of all things, drawn into a point with no size and infinite pull. What does this mean? Truthfully, we do not know. General relativity, the elegant theory Einstein gave us to describe gravity, breaks down at this singularity. The math spirals toward infinity. The numbers refuse to behave. It is as if the universe itself becomes silent, unwilling to show us what lies beyond. And perhaps that is the great secret of black holes. They're not merely destructive. They're not cosmic garbage disposals or violent monsters roaming the galaxies. They are boundaries, not of energy, but of knowledge. They show us where our understanding ends. They draw a line, not in the sky, but in thought, and dare us to cross it, to look deeper, to imagine further. The singularity may be real, or it may be a placeholder for some deeper truth, hidden by our incomplete physics. Perhaps quantum gravity, still unborn, will someday reveal a clearer picture. Perhaps black holes are not ends, but bridges. Perhaps there is something on the other side. But for now, we peer from a distance. We watch the death of massive stars scattered across the universe like ancient funeral pyres. Some of these stars have collapsed into neutron stars, city-sized spheres of degenerate matter spinning hundreds of times per second, but others fell all the way. And somewhere out there now in the cold between galaxies, they linger, motionless, lightless, and yet immeasurably powerful. For black holes, though invisible, shape the universe around them. They bend starlight, they distort orbits, they generate jets of particles that reach across interstellar space. And at the centre of nearly every galaxy, including our own, a supermassive black hole holds the entire stellar swirl in its grasp. These dark hearts are not rare, they are foundational. And so we begin our journey not with the strange, but with the necessary. The star collapsed, and in doing so, it gave birth to the most mysterious structure in the known cosmos. What comes next is the descent. There is a horizon in the universe that does not mark the end of space, but the end of return. It's not a surface, not a wall, not even something you could touch if you dared to drift toward it. It is a threshold, a pure boundary in the geometry of space-time, beyond which light, matter, and even cause and effect fall silent. This is the event horizon. To an outside observer, it is the black hole's defining edge, the line at which light no longer escapes, the last visible contour of something far more massive and mysterious. It is the surface we photograph when we image a black hole's shadow. The glowing halo of gas around it reveals the shape, not of the object itself, but of what we cannot see. Because the event horizon isn't a thing, it's a limit, a point of no return. From a distance it looks still, perfectly spherical, quiet. If the black hole is spinning, the horizon warps into a flattened sphere, but still, nothing stirs. No smoke, no movement, no flashing signature of death, just a cold, dark presence. Yet the physics unfolding at this invisible boundary is extraordinary. Imagine a spacecraft falling toward the horizon. To those on board, the fall continues smoothly. But to you, watching from a safe orbit far away, something strange happens. The closer they get to the event horizon, the slower they appear to move. Their descent becomes sluggish, as though dragged through molasses. This isn't an illusion, it's relativity. The gravitational field is so intense that it stretches time itself. The closer you are to a black hole, the slower your time ticks compared to someone farther away. Clocks run differently in strong gravity. And at the event horizon, from the outside perspective, time almost freezes. From your vantage point, the infalling ship never quite reaches the edge. It slows, redshifts, fades. The light it emits loses energy, shifts toward longer wavelengths. Its image stretches into infrared, then radio, then silence. The ship seems to hover, frozen forever at the brink. But this is only your view. From the ship's perspective, time feels normal. The crew sees the universe above them speeding up, galaxies spinning faster, stars aging in an instant. They pass the event horizon in finite time. No jolt, no shimmer, just an invisible crossing into a region where all directions curve inward. This duality, two truths, each valid, each irreconcilable from the other, is the strangeness of the event horizon. It marks a boundary not just in space, but in perception. It divides not only matter from matter, but story from story. For the outside world, the ship never falls in. For those aboard, they're long gone. This is what makes the event horizon so haunting. It is the place where physics begins to fork, where observers can no longer agree on what is happening, and neither can prove the other wrong. And yet the effects of this boundary ripple outward. A black hole's gravitational pull bends the very paths of light, creating gravitational lensing so intense that it distorts entire fields of stars. Background galaxies appear smeared, duplicated, wrapped around the void like the petals of a shattered rose. The black hole becomes a lens, not of glass but of space itself. This is why, when we photographed the supermassive black hole in the galaxy M87, what we saw was not the object itself, but its shadow. A ring of light formed by photons that had barely escaped. A perfect silhouette carved into a glowing storm of infalling matter. Even when black holes are quiet, when they are not feeding, they sculpt the motion of stars, gas and time. At the heart of our own Milky Way, stars whip around an invisible anchor. Too massive, too dark to be anything else. Their orbits, precise and fast, draw the outline of a gravitational abyss. And at the centre of that abyss lies a horizon. Not a surface, not a thing, but a limit. A place where time becomes curved beyond recovery. A veil that separates what can be known from what cannot. And so we watch from the outside, measuring distortions, tracing orbits, listening to gravitational waves echo from distant mergers, decoding silhouettes of what cannot be seen, and always the event horizon waits, silent, still, not a wall but a sentence, one that says, you may look, you may wonder, but you may not follow. The event horizon is not just a boundary in space, it is a rift in causality, a divide between two realms, one where influence, light, and communication are possible, and one where the concept of sending a message back has no meaning. To stand outside it and look in is to gaze at a kind of cosmic silence, a place where consequences never return. For the physicist, this boundary is defined with mathematical precision. It's the surface at which the escape velocity exceeds the speed of light. But for the poet, the philosopher, or the curious mind, it is something stranger, a veil through which reality is severed into before and after, inside and out, known and unknowable. Everything that passes the horizon is no longer part of the same future as the outside universe. And this isn't just theory. We see its fingerprints everywhere. The orbits of stars near Sagittarius A, the supermassive black hole at the heart of our galaxy, are not random. They trace out precise paths, slingshotting around something dark and massive, too small and too heavy to be anything but a black hole. Yet the thing itself cannot be seen, only inferred, measured not by light but by absence. The horizon cloaks it perfectly. But the black hole still speaks, not in words but in gravitational waves, ripples in the very structure of space-time, sent out when black holes collide. These waves, detected here on Earth, arrive as faint whispers in laser mirrors. They tell of titanic events, two black holes spiraling inward, merging, and briefly becoming something even more distorted before settling into a new horizon. No light reaches us from that moment, only geometry, only the aftershock of merging shadows. And the event horizon, it expands, it takes in the mass, the angular momentum, the energy. It grows as though reality itself is absorbing the cost of collapse. From the outside, we measure the change not in vision, but in shape, in the size of the shadow, in the warping of orbits, in the faint and distant waves of curvature rearranging themselves. It is easy to think of the event horizon as a kind of celestial membrane, a skin, soft and round, enveloping a core of mystery. But this is misleading. The horizon is not a surface on something, it is the something. The black hole is its boundary. The interior has no structure we can see, no coordinates we can agree on, no observation we can return. The moment an object passes through the horizon, its story, at least for us, ends. Its image freezes in place, its light fades, its signals redshift into silence, and yet the mass remains. The pull of gravity remains. Whatever it was, a planet, a spacecraft, a photon, a person, it now contributes only to the geometry. This is what the black hole keeps. Not the object, not the shape, only the properties that can bend space. And still, even knowing all this, there is a paradox at the edge. Because while nothing escapes the horizon, black holes do radiate. Stephen Hawking's work showed us that due to quantum effects near the event horizon, pairs of virtual particles constantly emerge from the vacuum. One falls in, the other escapes. Over time, this process causes the black hole to lose mass. It glows not with light but with heat. Faint, quiet, but real. This Hawking radiation suggests that horizons are not eternal, that they can shrink, that a black hole can eventually evaporate. But if it vanishes, what happens to everything that fell in? What happens to the information? This is the black hole's deepest mystery, and the paradox we'll explore in full later. For now, we are left with a surface that is not a surface, a boundary that is not material, and a silence that is not empty. A region in the sky that shapes the orbits of stars, bends the paths of photons, and marks a limit. Not just on what we can know, but on what can be known at all. To observe a black hole is to stand at the edge of a story that cannot be finished. To map a horizon is to sketch the edge of the unspeakable. And yet we try. We measure the shadows. We trace the warping of starlight. We listen for echoes in the trembling of space. And we wonder, if you could stand just outside the horizon, safe, suspended, silent, what would you feel? Would you sense the pull? Would you hear the shape of space itself? Or would it feel like nothing at all? No wall, no edge, no shimmer in the air, only the gravity of a secret, and the quiet knowing that beyond this veil there is no turning back. The most mysterious thing about the event horizon is how much it reveals. Because while no light escapes from within, the black hole is not invisible. It shapes the sky. It paints itself into the cosmos, not with colour, but with curvature. The closer you look, the more light betrays its presence. At a certain radius just outside the event horizon, photons can orbit the black hole in perfect circles. Not for long. These orbits are unstable, and any perturbation sends the light either spiralling inward or escaping outward. But for a moment, a photon can trace the equator of darkness. This is called the photon sphere. It is not inside the black hole. It is not part of the singularity. It is simply a location where the bending of space-time is so extreme that light, normally so stubborn and straight, curves all the way back on itself. And it is this structure, this tenuous, flickering halo of almost captured light, that defines what we see when we observe a black hole. When we peer into the void using radio telescopes the size of continents, as we did with the Event Horizon telescope, what we see is not the black hole itself. What we see is the chaos just outside it. Glowing gas spiraling inward, twisted by magnetic fields and spinning gravity. This glowing matter forms an accretion disk, orbiting at near light speeds, heating to millions of degrees, releasing radiation that our instruments can detect. And framed within this brilliance is the shadow, the silhouette of the event horizon, carved out not by what it emits, but by what it refuses to return. The light bends around the black hole, sometimes looping multiple times before reaching us. This creates a visual illusion, a ring larger than the horizon itself, a warped echo of the hole's geometry projected into our telescopes. This is the lensed image of a boundary. It is a horizon written not in ink but in photons that almost didn't make it. And yet the shape is unmistakable. It is perfect, circular, measurable. And from its size we can determine the mass of the black hole, its spin, its orientation. We can study what should be unseeable, not by crossing the veil, but by tracing the patterns it casts into the surrounding sky. Light, even when lost, leaves a signature, and the black hole becomes not a mystery hidden in darkness, but a lens of truth, a lens that bends not only images, but time itself. This gravitational lensing isn't confined to the inner disk. All around the black hole, space is warped like glass under pressure. Distant stars behind it appear doubled, stretched, ringed in arcs of light. These are Einstein rings, perfect circles of duplicated starlight caused by light bending around the black hole's frame. Even galaxies can be distorted by black holes that lie between them and us. We see them as smears, curves, or halos, ghosts of structure twisted by unseen mass, and so the black hole becomes visible not in spite of its darkness, but because of it. Its gravity reveals it. Its silence speaks. Even the absence, the perfect cutout in the fire of falling gas, is meaningful. It tells us where escape ends, where information is swallowed, where time begins to tilt. And this is the deepest paradox of the event horizon. It is defined entirely by what cannot leave it, and yet we know it exists. We've charted its edge, measured its size, listened to the symphonies of colliding horizons played out in gravitational waves, and still it evades touch. It remains a threshold of pure logic, a contour in the map of space-time, a point of no return, not because we lack the technology, but because the universe itself forbids return. We can observe a black hole for eternity, but we can never reach in and pull anything back. And so, with all our instruments and equations, what we've truly built is not a picture of the interior, but a portrait of the edge. The event horizon is a boundary we cannot cross, but one we can illuminate. And it reminds us, in physics, as in life, sometimes the most meaningful truths are revealed not by what you see, but by what refuses to be seen. Falling into a black hole is unlike any fall you've ever imagined. There is no wind, no sound, no surface rushing to meet you. You are weightless, free floating in a region where gravity has rewritten the rules. But gravity is not gone. It is everywhere. It is everything. You are not falling through space. You are falling with space, being carried along in a current of geometry that flows only one way, down. But not down in any conventional sense. Inside the event horizon, directions begin to lose meaning. What was once forward may now be inward. What once pointed out now curves in. Every path, no matter how you twist or turn, leads to the singularity. Imagine a fish swimming in a vast ocean current. No matter how it swims, the water carries it forward. The black hole is like that current, but one made of space itself. And you are no longer a swimmer. You are part of the flow. As the descent deepens, time begins to play tricks. Your clock ticks on, steady and calm, but if you could still see the outside universe, it would appear to race ahead. Stars swirl into fast forward. Millennia pass in moments. Galaxies merge. Civilizations flare and fade. To fall into a black hole is to become disconnected from the timeline you once shared with the cosmos. And yet, to you, nothing feels unnatural. You don't feel acceleration. There's no jolt, no sensation of motion, only the steady pull inward and the growing strangeness of your surroundings. Light behaves differently here. Rays no longer travel in straight lines. They curve, bend, spiral. Even photons, which once flew proudly at the universal speed limit, are caught in the inward flow of space-time. If you shine a flashlight ahead, the beam bends backward. Nothing escapes. Not because the black hole is actively grabbing light, but because the shape of space now offers no path that leads away. And still you fall. Behind you, the window to the universe continues to shrink. The last glimpses of the stars now gathered into a bright, distorted ring of blue-shifted light. Eventually, that too will vanish, not in a flash, but in silence. The outside world disappears not because it was destroyed, but because it has simply slipped out of reach. All the while the geometry around you is curving tighter. Distances contract, volumes collapse. You begin to notice something deeper, that the horizon wasn't just a boundary. It was a limit on communication, on cause and effect, on choice. Now everything is predetermined. There is only one destination left, the singularity. As you fall deeper, the meaning of distance begins to unravel. In the world you once knew, distance was simple. measured in meters, in miles, in the stretch between 2 points. But here those familiar reference points dissolve. The coordinates that once mapped the terrain of reality, up and down, left and right, past and future, no longer serve you. Because inside a black hole, space itself is no longer navigable. It's not just that you're falling through a curved region of space-time, it's that the very structure of space-time is collapsing with you. Every moment that passes carries you further inward. But what does inward mean when the space around you is shrinking? From the outside, the singularity lies ahead in space, but from your perspective within, it lies ahead in time. It is a moment in your future that cannot be delayed, cannot be avoided. The singularity is not somewhere you go, it is something you reach, the way you eventually reach tomorrow. And like all tomorrows, it is drawing closer with every tick of your clock. This is the most difficult concept to grasp, because our language is built for ordinary places, ordinary experiences. Inside a black hole, ordinary is gone. Geometry, which underlies all motion and all form, is being crushed. The curves of space grow steeper, the metric more extreme. The volume of any region shrinks. In some interpretations, the dimensions themselves begin to fold inward, until the space you occupy is no longer a three-dimensional arena, but something much stranger. If we could watch this from some transcendent perch beyond physics, we would see your world narrowing, not as a tunnel, but as a collapse of degrees of freedom. The ways you could once move, step forward, turn sideways, float upward, have all curved into one singular motion, falling inward, along the only direction space-time still offers. This collapsing space affects not just you, but everything that shares your fall. Matter compresses, fields intensify, radiation curves endlessly back on itself. Even the vacuum is distorted. Quantum fields, those invisible seas that ripple beneath existence, begin to surge and twist in the contorted geometry. Hawking once proposed that the vacuum near a black hole seethes with energy, virtual particles constantly forming and annihilating in pairs. But here in this interior realm, those processes are no longer symmetric. The sheer gradient of gravity disrupts them. What once cancelled perfectly now leaves remnants, contributing to the black hole's slow evaporation from the outside. Inside, the story is different. Inside, there is no evaporation, no reduction in mass, no loss of gravity, only accumulation. You are not alone in your descent. Everything that has ever fallen into this black hole joins you. Countless stars, clouds of gas, wandering debris, photons from ancient supernova, and perhaps other travellers like yourself. Their information, their trajectories, are still present in some form, encoded in the curvature, woven into the structure. And yet you cannot see them, not because they're gone, but because all paths lead in. The light they might emit cannot reach you. Even within the black hole, information cannot travel outward. It all tumbles together, compressed into tighter and tighter configurations, racing toward the same endpoint. And here in this narrowing world, you begin to sense something unnatural. Your surroundings, what little remains, are being stripped of meaning. Not just visually, but physically. The forces acting on you are changing. If the black hole is small, those forces are already growing violent. Your body, once whole, begins to stretch and deform. The gravity pulling on your feet is stronger than on your head. The difference intensifies second by second until your very atoms are torn apart. You become a stream of particles, elongated and accelerated by the steepening slope of space. But if the black hole is supermassive, the transition is slower, less traumatic. You might feel nothing at all. You may remain whole, intact, thoughtful, even contemplative, drifting in a shrinking bubble of space, time flowing onward, gravity rising like a tide beneath you. And still the singularity draws near. A singularity, not merely in the sense of something small, but in the mathematical sense, a place where the equations diverge, where values become undefined, where curvature becomes infinite. It is not a location, but a break in the fabric of reality, a flaw in the model, a place that should not exist, and yet does. At the singularity, all known physics collapses. Einstein's general relativity, so precise, so elegant, delivers infinities. Mass in zero volume, time in zero duration, space compressed to nothing. The numbers cease to make sense. Our models, stretched beyond their domain, surrender. And you, what becomes of you? Are you crushed into a point of zero size? Is your mass folded into the central distortion? Or do you continue, somehow, past the veil? We don't know. No one knows, because no theory yet unites the quantum world, the strange dance of particles and fields, with the gravitational fury of the singularity. Quantum gravity remains elusive. String theory, loop quantum gravity, holographic principles. Each offers hints, but none provide answers we can yet test. And so at the bottom of the black hole, we reach the bottom of our understanding. We know how stars die. We know how horizons form. We know what happens, until we don't. You are falling still, and ahead the singularity waits, a place where the universe holds its breath. You are moments from the end now, not the end of your body, though that too may come, not the end of your consciousness, though it is fading, but the end of space, the end of time, the end of meaning. This is the singularity. It does not exist in space because space itself has collapsed. It does not exist in time because time has been drawn inward and crushed into nothing. It is not a destination. It is not a thing. It is the absence of all frames of reference, the failure of geometry, the point where every equation we trust delivers an infinity. And still you fall. What does it feel like? No one knows, but we can imagine. Perhaps in these final instants, your sense of direction vanishes completely. Your surroundings shrink to a mathematical point. Time passes, and then doesn't. You reach a moment that has no before, no after. The timeline you followed through your life, your fall, your thoughts, ends in a breathless convergence. You are not torn apart in space. You're ended in time. If your mass, your particles, your structure still exist in some form, they now belong to the singularity. Their future is sealed, their data encoded in some hidden way, preserved perhaps in the deep architecture of quantum geometry, or maybe lost to the mystery forever. And here lies one of the great debates of modern physics. Does information die? Stephen Hawking once believed it did, that the black hole was the ultimate eraser, that anything which crossed the event horizon was not just destroyed physically, but erased from the fabric of reality, its properties lost forever, burned from the book of the cosmos. But this idea unsettled physicists, because in quantum mechanics, information must be preserved. The universe is not allowed to forget. So which is it? Does the singularity mark a true end? A final boundary beyond which identity, structure, and order dissolve? Or is it simply the beginning of something new, something we cannot yet name? Some believe that the singularity is not the end, but a passage, that just as the death of a star gave birth to a black hole, the death of space and time might give birth to something else, another region of the universe, another universe entirely. Some theorists describe black holes as bridges, Einstein-Rosen bridges, or wormholes, connecting two distant points in space-time, or even two separate realities. Could your fall, instead of terminating, transition? Could the singularity be a rebirth? Mathematically, the equations allow for it. But no one has ever returned to tell us. And so as you fall inward, past the final shimmer of distorted space, you face the ultimate silence. No signal can escape, no image can be captured, no second life can be confirmed. Only speculation remains. Perhaps your atoms are stretched into strings, wrapped across the boundary, their information preserved holographically on the event horizon itself. Perhaps you become part of a black hole's quantum memory, a data point inscribed in the curvature of space-time. Or perhaps not. Perhaps the singularity is truly an edge beyond which not even theory can tread, a mystery wrapped in gravity, held in place by the laws of physics, and pointing to a new law we have not yet uncovered. You have fallen as far as falling goes. What lies beneath your feet no longer exists. There is no further to go, And yet, even here, at the bottom of all things, there is wonder. Because you have reached a place no human has ever seen, no machine has ever mapped, no light has ever left. The place where knowledge ends. The place where the universe folds inward. The final moment is not an explosion, nor an impact. It is not pain or violence, it is disappearance. And as your journey vanishes into the singularity, a question remains behind, echoing in the quiet. What if this is not the end? What if this is the beginning? There is a way to see the universe that feels like poetry wearing equations. A way of describing reality not as a backdrop, but as something alive, malleable, responsive, ever curving. In this view, space is not a container. Time is not a clock. They are fabric, structure, texture. And gravity is simply the wrinkle. This is Einstein's revelation. Before him, gravity was force, a push, a pull. Something transmitted across distance, mysterious in its action. Newton described it beautifully, but he never explained what it was. Einstein did, or at least, he showed us how to think differently. That matter tells space-time how to curve, and curved space-time tells matter how to move. In other words, gravity is not an invisible hand reaching through the void. It is the shape of the void itself. And nowhere is that shape more profound, more dramatic, than around a black hole. Imagine a stretched sheet of fabric. Place a heavy ball in the center, and the fabric dips. Now roll a smaller ball across the sheet. It curves inward, drawn not by a force but by the contour of the surface. This is the standard metaphor, but it fails in scale. Because in space, the sheet doesn't bend downward, it bends in every direction. Not just space, but time itself is warped. And a black hole, it is not just a dip, it is a tear, a place where the fabric becomes so distorted that it folds into itself, creating a region from which no path leads outward, not even for light. This curvature is not theoretical, we have seen its effects. Starlight bends around massive bodies, its trajectory altered not by some particle exchange, but by the geometry of space it travels through. The first confirmation came during a solar eclipse in 1919 when the apparent position of stars near the Sun shifted, just as Einstein predicted. That was the beginning. Now we see this curvature everywhere, in the arcs of distant galaxies, gravitational lenses, where the light of entire clusters is stretched and magnified by invisible mass, in the orbits of stars near the Milky Way's center, moving as if whipped around an invisible anchor, in the waves of gravity themselves, ripples in the fabric of space-time, produced when massive bodies collide. We have detected those too. These waves, gravitational waves, are a new kind of vision. They do not come from light, but from the stretching and squeezing of space itself. And black holes, when they merge, send out these pulses. They are silent tremors of creation, carrying news of cosmic violence across billions of years. We have felt them on Earth, which means that the warped geometry of space is not an abstraction. It is real, it is measurable, and most important of all, it is everywhere. You're in it now. Your feet and your head, your thoughts and your heartbeat exist within curved space-time. Even standing still, you are moving through a distorted field. Gravity is not just the thing that pulls you to Earth. It is the Earth's shape embedded in the fabric of the cosmos. And yet, black holes go further. They are not merely curvatures, they're extremes, geometries so sharp, so deep, that they defy flat description. The equations that describe them are elegant and unnerving. They tell us that the closer you get to the event horizon, the more space and time exchange roles, that the radial direction becomes temporal, and the clock becomes a distance, that the interior of a black hole is not inside at all, in the ordinary sense, but ahead, something that lies in your inevitable future. This is not just poetic metaphor, it is literal math. The black hole's geometry reshapes what possible means. It redefines what a path is. It alters the relationship between cause and effect. The space-time diagram, a map of all possible events, begins to curve until light cones tip inward, causality collapses, and all futures point toward the singularity. And yet, from afar, the black hole remains still, perfectly spherical, quiet, defined by just a few numbers. Its mass, its spin, its charge. This is the no-hair theorem. The idea that black holes have no complexity on the outside. That no matter what falls in, stars, comets, dreams, it all becomes the same. It adds to the gravity. It smooths the shape. Only the mass remains. Only the geometry endures. And that geometry is a story told in silence. There is a strange beauty in simplicity. Black holes, for all their terrifying complexity, are described by so little. Mass, spin, charge, that's it. 3 values. No matter what intricate structures fall into them, no matter the shape, the colour, the texture, or the history, it all simplifies. The black hole absorbs, then forgets, or so it seems. But what if the smoothness is a disguise? What if the simplicity hides a code? The geometry of black holes is not smooth because it is empty. It is smooth because it is saturated. Saturated with curvature, with compression, with information pressed to the limit. The warping of space is not a void, it is a statement. It says, beyond this boundary, the rules you know are no longer valid. And that boundary is mathematical. Not a wall, but a horizon of predictability. Inside, the solutions to Einstein's equations curve towards chaos. Outside, the geometry is precise. And in between, the event horizon, is the line where our grip on reality begins to slip. But here's the deeper question. If black holes are shaped only by mass, spin, and charge, where does the rest go? Where does the information about what fell in? The angles, the trajectories, the composition, the entropy, where does that reside? For decades, physicists believed it was simply gone, that the geometry, warped so deeply, allowed the universe to hide its details forever. But quantum theory resisted. It insisted that information must persist. That reality does not simply delete its own history. And so the paradox emerged, a hole in our understanding, a contradiction between the 2 great pillars of modern physics, general relativity and quantum mechanics. The smooth geometry of space-time says one thing, the jittering world of particles says another, and caught between them, the black hole, the most curved object in the cosmos, and yet perhaps the most fundamental. Because in the black hole's geometry, we see a mirror of something deeper, not just a well in space-time, but a place where space-time reveals its structure, its limitations, its seams, and perhaps its connections. In recent years, new ideas have emerged, wild, beautiful ideas, that the event horizon is not just a boundary, but a canvas, that it stores information in its surface area, not its volume, that the entropy of a black hole is proportional to its surface, not its size. This is the holographic principle. The notion that everything within the black hole is somehow projected, encoded on its boundary, like a 3-dimensional object stored in 2, like memory written on skin, like a universe encoded on a surface. If true, this idea does not just rewrite our view of black holes, it rewrites everything. It suggests that the deep, warped geometry of space, its folds, its boundaries, its horizons, are not just side effects of mass, but clues to a deeper framework. That space and time themselves may emerge from information, from entanglement, from principles more abstract, more fundamental than gravity. In this vision, gravity is not the master law, it is the consequence. The bending of space is a byproduct of quantum threads connecting particles. The curvature of a black hole is the visible tip of a network of relationships, like tension in a web too fine to see. And so the black hole becomes not just an object, but a question. What is space? What is time? What is reality when the geometry that shapes it begins to fail? Because even now, as we orbit distant black holes with telescopes, as we model mergers and detect gravitational waves, the truth remains elusive. The singularity is hidden, the geometry is precise but incomplete, the map is not the territory, and yet the curve is everything. The universe is not flat. It bends with history, it bends with mass, it bends with memory. And perhaps in the deepest places where geometry breaks, we will find not chaos but a doorway, a new principle, a deeper symmetry, or maybe just silence, the silence of something vast holding its shape not through force, but through meaning. At the centre of every black hole lies something we do not understand. We call it a singularity, but that word is less an answer than a placeholder. It means only this: our mathematics has failed. Our theories have brought us here, guided us through the elegant curvatures of general relativity, across the warped terrain of space-time, past the shimmering veil of the event horizon, and now they break. Not from lack of precision, not from bad data, but from the arrival of infinity. At the singularity, the curvature of space-time becomes infinite. The tidal forces become infinite. The density becomes infinite. And the very quantities that once helped us describe the world, distance, mass, acceleration, time, become undefined. The equations don't simply misbehave, they fall apart. This is the end of the map, the place where space ends, not because it's bounded, but because space itself has been crushed into non-existence. Where time halts, not because it has run out, but because later is no longer a valid direction. And yet this collapse isn't visible. The singularity is hidden by the event horizon. Enclosed, veiled, cosmic censorship, some call it. The idea that nature hides its most violent truths behind horizons. That the singularity is cloaked for our protection. That its effects, while deeply felt, cannot be directly seen. We only know it's there because the math tells us it must be. But what is it really? A point? A filament? A region of quantum foam so chaotic and dense that it no longer resembles space at all? Perhaps the singularity is not truly a place in the ordinary sense, but a boundary of transformation. The moment when matter becomes undefined, when time becomes imaginary, when the fabric of reality undergoes a phase change. To the physicist, it's a region where our best tools, Einstein's general relativity, quantum field theory, no longer apply. To the philosopher, it's the edge of knowability, a reminder that the universe, for all its elegance, contains mysteries that no observer can pass through and return from. The singularity does not radiate, it does not shimmer, it does not rotate. It pulls absolutely, inescapably, not with force but with finality. It is the terminus of all worldlings, the convergence of all futures for those who fall within the event horizon. And here lies the greatest tension in modern physics. Relativity demands the singularity, its equations cannot avoid it. They tell us that once a sufficient mass collapses under its own gravity, a singularity must form. It is written in the mathematics of collapse. It is inescapable. But quantum mechanics refuses, because at infinitesimal scales, nature is jittery, probabilistic, discrete. Quantum theory says that infinities are not allowed, that energy levels must come in quanta, that space-time itself, if examined closely enough, should be grainy, composed of tiny loops, or strings, or informational nodes. And so the singularity becomes a battlefield, a point of contradiction, a place where the universe seems to say, you cannot go further with what you know. Not with gravity, not with light, not with reason alone. It is a place where certainty breaks down. And yet, that breakdown may be a clue. What if the singularity is not a failure, but a signal, a beacon, not to light, not to matter, but to the mind, a place where the universe folds in on itself, not to conceal truth, but to announce a deeper layer, one not drawn in curved lines, but in hidden symmetries, in subtle codes, because where the geometry collapses, something else might emerge. Many physicists believe that the singularity, as described by general relativity, isn't real in the physical sense. It's a warning flare, a sign that our model has been stretched beyond its limits, a sign that a new theory must take over. And so the search begins. We turn to quantum gravity, a theoretical framework we do not yet possess, but which we know must exist somewhere beneath the surfaces of both relativity and quantum mechanics. It must reconcile the smooth curves of space-time with the granular jitter of particles. It must explain how geometry behaves when it is forced into infinite compression. String theory offers one path. In this view, the smallest building blocks of the universe are not point-like particles, but vibrating strings, each with a tone, a frequency, a resonance. They dance not in 3 dimensions, but in 10 or 11, curled tightly into spaces we cannot perceive. And under certain configurations, these strings can prevent the formation of true singularities. Instead of collapsing into a point, the energy smears into a ring, a stringy fuzz, smoothing the harsh infinities into complex but finite structures. But string theory is not alone in this ambition. Loop quantum gravity offers another. Here, space-time itself is composed of loops, woven like a fine mesh, forming a granular fabric at the Planck scale. When a black hole forms, the loops collapse, but not into a singularity. Instead, they crunch into a compact, ultra-dense structure, a region of intense but finite curvature, perhaps even a bounce. Some theorists imagine that inside a black hole, space might collapse and then re-expand, birthing a new universe on the other side. A cosmic rebirth hidden inside every black hole, a seed that grows elsewhere. Then there's the holographic principle, a strange, beautiful idea that may hold the key to it all. It proposes that everything that happens inside a volume of space, every movement, every collision, every particle, can be described by information encoded on the surface of that volume. A kind of cosmic projection, a hologram, and black holes seem to obey this rule perfectly. Their entropy, the measure of information they contain, is proportional not to their volume, but to the area of their event horizon. Not what's inside, but what's on the edge. If this is true, then perhaps the singularity doesn't destroy information at all. Perhaps the details of everything that has fallen in are smeared across the horizon, preserved in a form we do not yet know how to read. Perhaps what looks like simplicity on the outside, just mass, spin and charge, is merely the compressed shadow of complexity. Perhaps the singularity is just a blind spot, and the real story is being written on the surface, but we are still learning how to read it. The information paradox remains unsolved. The singularity remains unseen. We cannot peer into it. We cannot send a probe nor shine a light. And so we theorize, we build mathematical scaffolds and dream our way into the gravity wells of collapsing stars. We run simulations and build particle colliders. We chase whispers in the cosmic background radiation. But the singularity waits, silent, absolute, and yet enticing. Because it is a boundary, yes, but also a doorway. The singularity is the place where physics declares its incompleteness, and where imagination must take over. It challenges us to ask not just what is, but what could be. Could information survive? Could new universes emerge from old ones? Could black holes be bridges, not graves? We don't know, but the singularity is not the end of inquiry. It is the beginning of wonder. The blank page at the centre of gravity's final sentence. It is where space-time ends, and meaning begins again. There is a kind of silence in the universe that isn't made of sound. It's made of uncertainty, a hush that settles not over the ears, but over the mind. A silence that grows louder the deeper we fall into black holes, because for all the mass they swallow, for all the stars they erase and the light they consume, black holes leave behind a question, a single question, that rattles the foundations of physics. What happens to the information? It is not a casual question. It is not philosophical fluff. It is a challenge, a direct strike at the two great pillars of modern science, general relativity and quantum mechanics. And the paradox it creates is unsolved. It begins simply enough. Imagine a book falling into a black hole, a real book, a novel perhaps, hundreds of pages, every sentence inked with detail, every word a choice. The book is information rich. It contains structure, history, order. Now throw it into the void. From the outside, all we observe is the book's mass, its angular momentum, and its electric charge, if it had any. Everything else is gone. The words, the language, the meaning, the complex arrangement of atoms that once made it a book vanishes into the event horizon. According to general relativity, the black hole absorbs this book without a trace. No smoke, no flash, just silence. The horizon grows slightly, its mass increases, but the book's internal information is lost, erased. But quantum mechanics does not allow this. According to the rules of quantum theory, information cannot be destroyed. No matter what happens to a system, no matter how it changes, evolves, decays, the information about its initial state must remain recoverable in principle. The universe is not permitted to forget, not completely. This is not a quirk, it's a law, as foundational as gravity. So when black holes seemingly erase the details of what falls into them, the contradiction becomes profound. We're forced to choose. Does gravity win and allow information to vanish? Or does quantum theory prevail and demand that somehow the information must escape? Stephen Hawking was the first to truly wrestle with this paradox. In the 1970s, he proposed something startling. Black holes aren't completely black. They aren't eternal. They emit radiation, what we now call Hawking radiation. This radiation arises from quantum effects near the event horizon. In the strange vacuum of curved space-time, virtual particle pairs flicker into existence. One falls in, the other escapes. The black hole loses mass. It evaporates, slowly, over unimaginable timescales. And eventually, it vanishes. Here lies the twist. Hawking's radiation is thermal. It carries no information. It's random, meaningless, just heat. So if the black hole disappears and all that remains is this featureless glow, then the information about the book, the atoms, the words, the structure, is truly gone. Lost, which violates the rules of quantum mechanics. This was the crux of the black hole information paradox, a problem that sparked decades of furious debate, countless papers, and some of the most creative thinking in theoretical physics. Was Hawking right? Could information really disappear? Or was there a deeper structure hiding behind the event horizon? Some physicists argued that the information was somehow encoded in the Hawking radiation itself, that while the radiation seemed random, it actually carried subtle correlations, like a scrambled signal waiting to be decoded. Over time, as the black hole evaporated, the complete pattern might emerge. Others proposed the idea of black hole complementarity, that from the outside, information never truly enters the black hole, but instead is stored on the horizon, smeared across its surface in a kind of cosmic ledger. For an external observer, the information never crosses the threshold. For an infalling one, it does. Both are true, both are consistent. No contradiction arises, because no single observer can see both stories. But the most daring idea came from the world of string theory. There is a paradox at the edge of every black hole, a flame where there should be silence. It begins with an effort to save unitarity, to protect the sacred rule that information must never be destroyed, to reconcile Hawking's thermal radiation with the structure of quantum theory. Because if black holes truly erase the identity of what falls in, then the universe itself loses its memory. The past no longer leads to the future. The laws of physics become optional. And so, theorists began to dig deeper, searching not for new particles, but for a new way to look at reality. What they found was unsettling. In 2012, a group of physicists, Almhiri, Marolf, Polchinski, and Sully, proposed a thought experiment that exploded across the field. They tried to resolve the contradictions between relativity, unitarity, and the smooth experience of falling into a black hole. But the equations didn't add up. One of the assumptions, they realized, had to go. And so, with reluctance, they let go of one of Einstein's most cherished principles, the idea that the event horizon is uneventful. In general relativity, crossing the horizon of a large black hole should be painless, smooth. A free-falling observer wouldn't notice anything unusual. No walls, no burns, just the quiet continuation of space-time. But to preserve unitarity, if the Hawking radiation really carries information, and that information is entangled with what remains behind, then something has to give. The entanglement must be broken. And breaking entanglement isn't subtle. It has consequences. It creates energy. It creates fire. Thus was born the firewall paradox. The idea that the event horizon, rather than being smooth and passive, is actually a blazing boundary, a searing sheet of high-energy particles, a place wherein falling matter is incinerated. Not gradually, not at the singularity, but right at the edge, a firewall. This is shocking. It violates the equivalence principle, Einstein's foundational notion that free fall is indistinguishable from rest. It says that space-time can no longer be trusted to behave, that gravity's gentleness ends not in the centre, but at the surface, and that the experience of falling in is not quiet, but catastrophic. Physicists were divided. Many resisted the idea. The firewall felt like a brute force fix, a patch on a puzzle that deserved elegance. But it made the stakes clear. If black holes preserve information, and if that information escapes via Hawking radiation, then something radical must happen at the horizon. Either you lose the principle of equivalence or you lose unitarity, or both. But another idea was already gaining ground. A deeper, stranger idea. One that seemed at first like science fiction, but which began to gather mathematical weight. The holographic principle. It suggests that everything we think of as volume, everything inside a black hole or a galaxy, or even a room, might actually be encoded on a lower dimensional surface. That the true degrees of freedom don't live in the bulk of space, but on its boundary. Imagine a three-dimensional world, projected from a two-dimensional screen, like a hologram. This idea found its strongest footing in ADS-CFT correspondence, a breakthrough from string theory proposed by Juan Maldacena. In this framework, a gravitational universe in higher dimensions is exactly equivalent to a quantum field theory living on its lower dimensional boundary, without gravity. Two radically different descriptions. One reality. This duality suggested that black holes could be fully described by the information encoded on their horizons, that the entropy of a black hole, the famous Bekenstein-Hawking formula, was not just symbolic, but literal, that the horizon is the memory, that the interior of the black hole is emergent, not fundamental, that everything you think of as inside the event horizon is a projection of the information stored on its surface. And if that's true, then there may be no contradiction after all. The information never falls in. It never has to escape. It was always at the edge, encoded, encrypted, preserved. Even as the black hole radiates and shrinks, the information is released, gradually, subtly, through patterns in the Hawking radiation. At first, the radiation looks thermal, but over time, structure emerges. Correlations appear. The signal reassembles. The puzzle unravels. This is the Page curve, a theoretical prediction for how information recovery behaves over time. In the early stages, radiation carries no information. But as more of the black hole evaporates, the curve bends. The information begins to return, slowly at first, then accelerating, until in the final flickers of radiation, all that was lost is found again. But if this is true, then the horizon is not fire, it is code. And the black hole is not a destroyer. It is a vault, a region of curved space so extreme, so precise, that it compresses complexity into silence, but not into oblivion, into storage. This idea is poetic, profound, and still unproven. We do not yet know whether firewalls are real, or whether holography can truly decode every lost past. We do not know whether Hawking's paradox is solved, or merely transformed into new mysteries. And we do not know what happens in the final moments, when the black hole, shrunken to a whisper, finally vanishes. Does the information emerge in full, or does some part remain, a cosmic remainder, a seed, a door? For now we remain on the edge, watching, wondering, listening to the soft crackle of paradox at the borders of our understanding. The black hole still radiates, still curves, still holds its silence, but perhaps just beyond that horizon, the universe remembers. What if falling into a black hole isn't a dead end? What if it's a tunnel? This idea, daring, elegant, and ancient in its appeal, has captured imaginations since the earliest days of general relativity. The equations allow it. The physics does not forbid it. The black hole, rather than being a cosmic terminus, could be a bridge, a passage through the folds of spacetime, a wormhole. These hypothetical structures, called Einstein-Rosen bridges, emerged from the mathematics of Schwarzschild geometry. In 1935, Albert Einstein and Nathan Rosen explored solutions to the equations of general relativity and discovered something extraordinary. The interior of a black hole could be mirrored, forming a connection between two separate regions of spacetime, a tunnel buried inside geometry. But even then, there were complications. The Einstein-Rosen bridge, as first described, was unstable. It pinched off too quickly. It couldn't be crossed. A traveller would never make it through. It was like finding a door in the universe, only to realise it closes the moment you touch it. Still, the idea lingered, evolved. Later models proposed new kinds of wormholes, some traversable, others still forbidden. The mathematics grew richer, the diagrams more elaborate. Could exotic matter, material with negative energy density, stabilise a wormhole's throat? Could quantum effects keep it open long enough for something, or someone, to pass through? Maybe, but speculation turned bolder still. In 2013, a new idea appeared on the horizon of physics. It was short, simple, and possibly revolutionary. ER equals EPR. The proposal came from physicist Juan Maldacena and was refined with Leonard Susskind. It suggested that wormholes, Einstein-Rosen bridges, are not merely allowed by the equations, but are equivalent to another, entirely different phenomenon: quantum entanglement. EPR refers to Einstein-Podolsky-Rosen, the famous trio who once challenged the completeness of quantum mechanics. In their 1935 paper, they described a strange phenomenon where two particles, separated by vast distances, could remain mysteriously linked. Measure one, and you instantly affect the other. Spooky action at a distance, as Einstein called it. But what if that spookiness is a bridge? What if entanglement, the most mysterious connection in quantum theory, is literally a wormhole in disguise? ER equals EPR says this: every entangled pair is connected by a quantum bridge. Maybe not one that matter can travel through, but one that structure, information, or correlation does. In this view, the geometry of spacetime emerges from a vast web of entanglements. Gravity itself may arise from these threads. If this is true, it changes everything. Black holes, already heavy with mystery, become knots in the quantum fabric. When two black holes are entangled, they might be connected, literally, by a wormhole. Their interiors could be the same space, and if information falls into one side, perhaps it can be retrieved from the other. This is not fiction, it's not fantasy, it's math. And though we cannot yet build a wormhole, we may already be observing their effects. In the entanglement of black holes, in the correlations of Hawking radiation, in the structure of holographic dualities, every equation whispers the same possibility. Space-time is woven, not built. And black holes, they are tangles in that weave, gateways maybe, or mirrors, or folds. And though we cannot yet pass through them, we can wonder, if a traveller were to fall into one end of a wormhole, what would they find on the other side? Another black hole, another galaxy, another universe? Or something far stranger, an echo of their own past, a closed time-like loop, a Mobius path through the architecture of cause and effect? To imagine a wormhole is to imagine a crack in the architecture of distance. A tunnel not through space as we know it, but through space as it could be, folded, bent and reconnected in ways we are only beginning to grasp. If the universe is a sheet, then a wormhole is a shortcut drawn by folding that sheet in half. What once required light years to cross now takes a single step. But this shortcut, if it exists, is not empty. It is not like a subway tunnel or a cosmic drainpipe. It is geometry, living geometry, warping as you move through it. The walls of the wormhole are not material. They are space-time itself, twisted into a corridor. and every traveller who enters would become part of that structure, bending with it, bound to its delicate curvature. What would the journey feel like? No one knows. Some models suggest the interior of a wormhole could be navigable, smooth, even serene, a silent glide through a curved space where no external stars shine. Others suggest violence, tidal forces, and radiation spikes so intense that even atoms would be torn apart. The difference lies in what stabilizes the tunnel. Because here's the challenge. Wormholes by default collapse. Left alone, their throats pinch off faster than any ship or signal could traverse them. Gravity closes the path almost instantly. To keep it open requires something exotic, negative energy, matter that doesn't behave the way normal matter does. It doesn't fall, it doesn't radiate, it pushes outward against curvature. And yet, we don't know if such matter can exist in the required form or quantity. Quantum effects might allow it, through something called the Casimir effect, where empty space itself generates a pressure due to vacuum fluctuations. In carefully arranged conditions, negative energy appears, tiny, fleeting, perhaps in some future era harnessable, but for now, wormholes remain theoretical. Still, the mathematics offers dazzling possibilities. In some solutions, a wormhole connects not two distant places in space, but two different moments in time. A time machine of sorts, not by violating the speed of light, but by bending causality into a loop. In others, the bridge connects two entirely different universes, each with its own history, its own constants, its own physical laws. The throat of the wormhole becomes a border crossing between realities, and in the boldest models, wormholes are not rare, they're everywhere. If ER equals EPR is correct, if every entangled particle is connected by a Planck-scale wormhole, then the universe is riddled with microscopic bridges, too small to see, but essential to the very structure of space. Like the weave of a tapestry, invisible from afar, but holding the fabric together. In this view, space-time is not a backdrop, but a network of entangled bits, of quantum links, of countless tiny wormholes binding the universe into coherence. And black holes? They're not exceptions. They are the manifestations of that network made large, macroscopic wormholes perhaps, singular entanglements grown so massive they warp not only particles, but light and time. Some suggest that the interiors of black holes, those regions hidden beyond the event horizon, are actually made from entangled radiation. That space doesn't exist there in the traditional sense. It emerges from the connections between degrees of freedom stitched together by entanglement. You cannot touch the walls, because there are no walls, only relationships, only information, only bridges. This view is radical, but it is not unscientific. From string theory to ADS-CFT duality to quantum gravity, the math begins to converge on a strange idea, that space is not fundamental, that it arises from something deeper, that wormholes and entanglements are not oddities, but clues. Clues that everything we know, light, motion, gravity, geometry, may emerge from how the universe remembers itself. So when you think of a black hole, don't imagine a dead star. Imagine a thread, a doorway, a place where information passes not outward but inward, through invisible corridors to other locations or other layers of reality. Perhaps somewhere on the other side of a black hole there is a beginning. Perhaps when one universe ends, another is born. Perhaps the collapse of space in one place births the expansion of space in another. We don't know, we may never know, but the bridges are there, in the equations, in the geometry, in the dreams of every physicist who stared too long into the dark and wondered, what if the whole is not an end? What if it's a path? There are places in the universe where questions end, not because we found the answers, but because the questions themselves no longer make sense. Places where the structures we rely on, space, time, matter, causality, begin to fade like mist in morning light. These are not regions of destruction. They are not chaos. They are the edge of reality. And black holes are that edge. We've traced them from beginning to end, from the death throes of massive stars to the silent curtain of the event horizon, into the warping depths where time curves and matter folds, toward the singularity itself, where geometry fails and infinity knocks on the walls of logic. And after all of it, one thing remains: wonder. Black holes are not just astrophysical objects, they're invitations. Each one is a riddle written in space-time, a challenge, a mirror. They show us not only what the universe is, but what we don't yet understand. And more than that, they show us what kind of creatures we are. Because we did not look at the night sky and shrink away. We looked at the darkness between the stars and asked, what lives there? We followed gravity into its deepest silence. We listened to the tremors of invisible collisions. We wrote equations to map the edge of existence. And we imagined what might lie beyond. In black holes, we see the death of stars. But we also see the possibility of rebirth. A collapsed point in space-time may also be a tunnel, a vault, a seed. In their terrifying simplicity, black holes erase detail, and yet they contain everything that has ever fallen into them. Even meaning, even memory. The firewalls, the bridges, the paradoxes, and projections. Each theory is a stepping stone, reaching towards some deeper truth. Whether that truth is quantum, geometric, or entirely beyond the languages we speak today, we do not know, not yet. But it is out there. The universe is vast, not just in distance, but in depth. And black holes are proof that depth matters. They remind us that not all silence is empty, that not all shadows are absence, that the darkest regions of the cosmos are often the places where the light of understanding burns the brightest. So let this story stay with you, not just as a scientific journey, but as a meditation. When your eyes close and the world begins to quiet, remember that even the smallest mind can hold the universe. Even the gentlest breath can carry you across the stars. And even now, beneath your thoughts, gravity whispers, a soft pull, constant and quiet, not to destroy, but to draw you inward, toward stillness and toward rest, toward the edge of what is known. And there, where the questions end, let sleep begin. Thank you for joining us, Voyager. If this journey brought you peace or wonder, a like or a comment helps us reach others drifting in the dark. Until next time, sleep well and keep falling towards the stars.